After we saw in the previous video how Max Planck solved the ultraviolet catastrophe through the quantization hypothesis, we will now move on to see how the idea of quantization of light or its particle property, in addition to its wave nature, was strengthened. At the beginning of the 20th century, Albert Einstein saw what Planck had done as very important, and demanded that the idea of quantum be generalized to all optical and electromagnetic phenomena and not just to thermal emission. Besides the ultraviolet catastrophe of thermal radiation, there was also a problem intractable to classical physics: photoelectric emission. In some metals, such as cesium, when light is shined on its surface, we see that an electric current has passed in the circuit connected to this metal. This current started instantaneously after shining light on the metal surface and without a time interval. The electromagnetic theory could not explain this matter because light in it is waves that occupy a relatively wide spatial space. This is a fundamental wave property. Therefore, this wave energy is also distributed over a spatial area. When light falls on the surface of the metal, the wave will cover several electrons located near the surface of the metal. Each electron will only take up a small portion of the wave's energy. It must take time to store energy in the metal so that the electrons can move and create a current. Albert Einstein adopted Max Planck's quantum idea and saw that actually the photoelectric emission of electrons occurs at a certain frequency of light. At low frequencies, this effect does not occur. Only when the frequency of light is greater than a certain value do we get the emission of electrons from the metal's surface and thus obtain a current. Since one quantum from Planck's hypothesis was an amount of energy equal to h times the frequency, f, if such quanta with the appropriate frequency f fell on the surface of the metal, it would directly cause the release of electrons from the metal. In other words, the energy of light is not spread continuously over space, as in classical electromagnetic theory, but rather quantized into quanta. Hence, when a quantum with the appropriate energy meets an electron, it will be absorbed and the electron will be able to be released. Because the electron is inside the surface of the metal, it will use some of this quantum energy to first exit the metal. This energy is called the work function, and it varies depending on the metal. The remaining energy is the kinetic energy of the electron, allowing it to move outside the metal. So the equation becomes: the final electron kinetic energy is the energy of the absorbed photon minus the work energy required to free the electron from the metal. If we graph this equation where the x-axis represents the frequency of light and the y-axis represents the kinetic energy of the electron, we will see that we get a straight line. The point of intersection with the x-axis is the threshold frequency from which the photoelectric effect begins. Here, the point of intersection with the y-axis represents the work energy required to release the electron from the metal. It represents the binding energy of an electron within the metal. It was also possible through this graph to calculate the constant h that appears in quantum energy, and as we can see, h is nothing but the slope of the graph line. So, contrary to the classical theory that the energy of a light wave will be distributed among several electrons inside the metal surface, each electron actually absorbs the entire quanta of light, and thus simultaneously receives an amount of energy proportional to the frequency of this light. This quantization also explains why the intensity of incident light affects the intensity of the current. Increasing the intensity of light doesn't mean that the energy of a single quantum or its frequency increases. Rather, it means that the number of quanta is greater. Since each electron absorbs one quantum, there will be an increase in the number of electrons, and consequently, an increase in the intensity of the current. This revolutionary explanation of the photoelectric effect was good proof that the energy of light, or electromagnetic radiation in general, is quantized. There is still a further step towards fully confirming the particle aspect of light, namely the property of collisions and momentum exchanges that appear in particles in general. Thanks for watching.